Welcome back. In this lecture, we will cover the introduction to boundary layer flows. When we non-dimensionalize the governing equations of a flow and for the variable x and z, the spatial coordinates, we non-dimensionalize with the characteristic length of the body. In the case of flow past a cylinder, we use the diameter of the cylinder as the characteristic length and define x star is equal to x by d and z star is equal to z by d. We use tau as a characteristic time and define t star as t divided by tau. The velocity component u and w are non-dimensionalized with respect to the amplitude of the free stream velocity V naught. The pressure is non-dimensionalized with P naught, the free stream pressure. And when we do this, the governing equations take these forms. We have simplified the momentum equation by making the coefficient of the convective acceleration 1. Then these are to be solved subject to boundary condition. V star tends to sin t star I as x star and z star tends to far upstream or far downstream. V star is 0 on the surface of the cylinder and P star tends to 1 as Z star tends to 0 and X star tends to infinity. The first term in this is the unsteady acceleration term. The second term is the convective acceleration term, and on the right hand side the first term is the pressure term, the second term is the gravity force term, and the third term is the viscous force terms, as we have discussed before. On introducing the non-gravitational gauge pressure, script P is equal to P plus rho gz minus P naught, the pressure and gravity terms combine to give delta P naught divided by rho V naught square times del star P star. And then the momentum equation acquires this form. The coefficient of the first term is this whole number. The coefficient of the first term on the right hand side is 1 over Euler number, and the coefficient of the last term is recognized as 1 over Reynolds number. If Reynolds number is large, that is, if we are considering a high Reynolds number flow past an immersed body, then we can neglect the viscous terms. And that leads us to the Euler equation. The Euler equation can be solved relatively easily. We cannot apply the no slip condition at the boundary. This gives potential flow about the body, and as seen before, this leads to zero drag about a two-dimensional body. This Euler equation has been applied to aerodynamics, and when we apply it to aerodynamics, we are able to predict lift coefficients defined as CL is equal to lift divided by 1/2 rho V naught square times the area that characterizes the aerofoil, and we find that this is of order 1. This matches quite well with the experimental results. This predicts the drag coefficient CD to be exactly 0. Since the experimentally obtained drag coefficient is of the order of 1 over a square root of Reynolds number. This is quite acceptable result. And therefore, Euler equations is applied routinely to obtain the first estimates in aerodynamics. However, when you apply to bluff bodies, it again predicts drag coefficient or to be exactly 0. But experimentally, we obtain the drag coefficient of order 1. This leads to a paradox that is known as D'Alembert's paradox. D'Alembert in 1749 concluded, "It seems to me that the theory developed in all possible rigor gives, at least in several cases, a strictly vanishing resistance for drag, a singular paradox which I leave to future geometers to elucidate." Kirchhoff and Rayleigh applied the free streamline theory to solve flow past bluff body. The model predicts correctly that the drag varies like the square of the velocity and obtains the drag coefficient of order 1, but the value is too low. The value they obtain for a flat plate held normal to the flow is 0.88 versus 2.0 as obtained by experiments. Further, the vortex sheet in the wake should be unstable. This theory, however, has been used to predict drag in cavity flows where vacuum is assumed in the wake. Prandtl in 1903 put forward the idea that the high velocities and high Reynolds number, the no-slip boundary conditions causes a strong variation of the flow speeds over a thin layer near the wall of the body. In this picture, we have water flowing past a flat plate held parallel to the flow. Hydrogen bubbles are produced upstream by passing current through an electric wire. The tiny hydrogen bubbles make the flow lines visible, and we see very close to the plate in a thin region relative absence of hydrogen bubbles. Then in 1977, Wortmann used a tellurium electrode in water. When the current passes through the tellurium electrode, a colloidal cloud is produced and it is swept down with the velocity of flow very close to the plate. He obtained the picture of the flow after a small time. So that this curve that you see represents the velocity profile of the flow past a flat plate. This photograph confirms that the no-slip condition at the wall is met even in very high Reynolds number flows. Prandtl has also taken a sequence of photographs for flow past a cylinder in water. The flow starts from rest, starting from the top left. Going down, we see just as the flow starts, the flow picture is very close to the picture of an ideal flow, that is, picture of the potential flow. It is only as the time develops, the boundary layer grows around the cylinder and starts separating at about this picture that we get the flow that we see as steady past a circular cylinder. This established that there truly is a boundary layer near the front of the cylinder, and that it separates from the cylinder in the latter half of the cylinder. The power of Prandtl's formulation was in its ability to explain the large drag coefficients observed on bluff bodies. The rapid change of flow speed near the wall leads to generation of the vorticity there and to the viscous dissipation of kinetic energy in the boundary layer. The energy dissipation, which is lacking in the inviscid theories, results for bluff bodies in separation of flow. In this picture of flow past a sphere, the flow is water, and we use an electrode around here wrapped around the sphere. As the electric current passes through this electrode, a cloud of hydrogen bubbles is created, and we take a picture of the cloud as it forms. It clearly shows the separation of the flow at around this location. As discussed earlier, the flow here is laminar. This separation results in complete disturbance of flow in the wake of the sphere and leads to large drag, as will be explained in this lecture. Prandtl started his development by stating that the region in viscid flow cannot extend right up to the wall. He formulated a thin region adjacent to the wall where viscous forces are not negligible and are significant. The velocity changes rapidly across this thin layer from the no slip at the wall to the required inviscid flow velocity at the outer edge of this region. Consequently, the velocity gradient perpendicular to the wall should be normalized not by the characteristic length of the body, but by the thickness of this layer. Let delta sub c be the characteristic value of this thickness. A thin boundary layer is developed around a body. The thickness shown here is quite exaggerated, but to see clearly what is happening, we take a small element of the surface and enlarge it. Typically, the velocity changes from 0 at the wall to a value close to what is predicted by the inviscid flow in the outer region outside the boundary layer. Let the coordinate along with the flow direction be x, and perpendicular to this point at the surface is y. And then, while non-dimensionalizing, we use L, the dimension of the body, as the characterizing length for the x coordinate, but for the y coordinate we use delta c, the length characterizing the thickness of the boundary layer, so that we define a non-dimensional coordinate eta as y divided by delta c. The u component of the velocity is characterized by v naught, as is the v component. And if we apply this non-dimensionalization to the continuity equation, we get L by v naught del u star by del x star plus del by v naught times del v star by del eta is equal to 0. Since both terms are to be significant in this continuity equation, we cannot have delta u star by delta x star tending to 0 as well as delta v star by delta eta tending to 0. The characteristic velocity in the y direction should be like v naught delta by L rather than v naught, so that the two terms become of the same order. If we do this and use v superscript O, that is VO, as the non-dimensionalized velocity in the y direction, v divided by v naught delta c over L. We use a different symbol for the non-dimensionalized vertical velocity v, because we do not want it to be confused with the characteristic velocity v naught. So that now the continuity equation gives del u star by del x star plus del v naught by del eta is equal to 0. Thus, with this non-dimensionalization of velocity and the vertical space coordinate, we get the proper form of the continuity equation where both terms are significant. Let's now work with the x momentum equation for the boundary layer. Assuming that the flow in boundary layer is laminar, so that we can use the appropriate form of the Navier-Stokes equation for steady flows, and if we non-dimensionalize it using delta c for the distances normal to the surface and v naught delta c divided by L as the velocity in the normal direction. This is the equation that we get. We simplify by dividing across by rho v naught square by L, and we get this equation. Here we have delta P naught as the characteristic pressure difference in the x direction. We notice that delta P naught by rho v naught square is like 1 over Euler number. Mu over rho v naught L is like 1 over Reynolds number. And the coefficient of the last term is simplified to 1 over Reynolds number times L square by delta c squared. We notice here that 1 over Reynolds number is very low compared to 1, which are the coefficient of the convective acceleration term, and can be neglected from this equation. Of course, this term needs to be retained, because if this term also is neglected, then we'll get back the Euler equation, and that will not suffice for the bounded layer flow. We can retain this equation because delta C is as yet unknown. We choose the value of delta C such that the coefficient of this last term is of the same order as the convective acceleration terms, which is order 1. So, letting the order of this last term to be 1, we get delta C over L to be like 1 over under the root Reynolds number. That is, the boundary layer is characterized by a thickness which is 1 over under root Reynolds number times the length scale of the body. For large Reynolds number, this could be a small fraction of the body length, and that's why we say that the boundary layer is thin. This is an important result. We have been able to obtain an estimate of the boundary layer thickness with very little mathematics and without solving any equation. We also conclude that since 1 over Euler number should be of order 1, therefore, the pressure differences in the x direction should be of order rho v naught square, the same as the pressure differences we obtain in the Euler equations for the inviscid flow. This, to repeat the result, we get delta C over L is like 1 over Reynolds number, and the pressure differences are of order rho v naught square. Now, let's work with the y momentum equation for the boundary layer. And if we non-dimensionalize using the same definition of the non-dimensional variable as before, we get this equation. And when we simplify this equation, we get this equation where the first term and the second term, the convective acceleration terms, have been rendered of order 1. Notice that the first term on the right hand side is of order Reynolds number, because delta P naught by rho V naught square is of order 1. And if we do this, then L square by delta C square is like Reynolds number. The second term on the right hand side is of order 1 over Reynolds number, and the third term, the last term, is of order 1. Thus, for large Reynolds number is the pressure term that is dominant. And from this, we can conclude that delta P normal to rho V naught square should be of order delta C by L whole square, that is like 1 over Reynolds number. That is, if we use delta P naught as the delta P naught we obtained earlier in the x direction, then this term becomes too big and the delta P star by delta eta is 0. So, to the order of rho V naught square, pressure changes in the normal direction are negligible. But the characteristic pressure difference in the normal direction, delta P naught normal, is like 1 over Reynolds number of the pressure difference in the streamwise direction, that is rho V naught square. Thus, the characteristic pressure difference in the normal direction is like 1 over Re of the characteristic pressure difference in the streamwise direction, that is very small and negligible. Prandtl neglects this pressure difference totally, and so the y momentum equation disappears and del P by del x in the x momentum equation replaced by minus dP by dx. Assumed that within the boundary layer the pressure varies only in the x direction. There is no variation of pressure in the y direction. It is an assumption on which the theory of aerodynamics is built up. The boundary condition for these equations is that at the wall u is equal to 0. At the outer edge, the streamwise component of u tends asymptotically to the value capital Ux. That is the velocity in the outer flow at the edge of the boundary layer. This velocity capital U of x is obtained from the Euler equation. So, this is the solution of the inviscid potential flow in the outer layer, the flow region outside the boundary layer. Since the boundary layer is thin, we may extend the outer flow to the wall itself without much error. The pressure determined at the wall from the inviscid flow is impressed on the boundary layer. In the inviscid flow, dP by dx at the wall is like rho u du by dx, and therefore the x momentum equation for the boundary layer becomes this. So, the equations for the boundary layers are the continuity equation and the x momentum, and this represents considerable simplification. We have dropped one equation. So, instead of 3 equations, we have now 2 equations within the boundary layer. Now, there are only 2 unknowns, u and v. The pressure has been solved from the inviscid flow equation and is put there. So, instead of 3 dependent variables, we have only 2 dependent variables. Also, and this is of great importance, that we have dropped the second order derivative with respect to x in the x momentum equation. This changes the character of the partial differential equation. Those of you who are familiar with the theory of partial differential equation will realize that this change in character of this equation is a very significant change. The equation has become parabolic instead of an elliptic equation. Solving of parabolic equation is relatively easier than the solution of elliptical equation. And this is what was achieved by many students of Pradhan who did head calculations of calculating the boundary layers. A parabolic equation is like a heat equation which can be solved by marching in time. In this case, in marching along x, starting with the flow at x is equal to 0 or at an initial point. So the process is we solve the outer flow neglecting the boundary layer completely. Though the outer flow is only up to the edge of the boundary layer, but since the boundary layer is thin, while doing this calculation, we calculate the outer flow right up to the boundary of the body. Once we have solved for this outer flow, we obtain dP by dx at the wall as minus rho capital U du by dx in the outer flow at the wall. Here capital U represents the flow-wise velocity at the surface of the body after neglecting the boundary layer. Now, this dP by dx is now impressed on the boundary layer itself. We imagine that across the boundary layer, the pressure does not change in the y direction, in the normal direction. And therefore, whatever be the dP by dx obtained as the edge of boundary layer is the dP by dx across the boundary layer. Now we solve the boundary layer with the condition that U tends to capital Ux, the inviscid velocity, the potential flow velocity, asymptotically as y within the boundary layer tends to infinity. And the other boundary condition is that there is no slip at the wall, y is equal to 0. Once we can solve for this, we can calculate for the quantities of interest such as shear stress along the wall and skin friction, etc. Note that the following assumptions have been made so far. The thickness scale of the boundary layer is very small in comparison to the length scale of the outer flow. This is ensured if Reynolds number based on the scale of the body is large. A value of the Reynolds number of 10,000 gives delta C by L of about 0.01. That's only 1%. In most flows of interest, the Reynolds number is higher than 10,000. So delta C by L is smaller than 1%. The second assumption that we made is that the outer flow pressure is impressed across the boundary layer up to the wall. And this requires that the curvature of the wall is small. If the curvature of the wall is small, then we can neglect that curvature. And this condition is met when the radius of curvature is much larger than the thickness of the boundary layer. So except for a very small radius we can neglect the curvature of the surface and treat boundary layer as on a flat surface. We also assumed that the flow is laminar, so that we can use the form of the Navier-Stokes equation, which is valid for laminar flow. That is, with Stokes' hypothesis for the stresses in the body. If the Reynolds sum is too high, the boundary layer turns turbulent, and this formulation would not be valid. We have also assumed that the flow has not separated from the wall. It is an important condition because once the flow separates from the wall, it is no longer thin. The boundary layer is no longer thin, and the total boundary layer assumptions break down.